Hello and welcome back to Math 112, Calculus 2. Today we have Lecture 18. Our topic for today is partial fraction decomposition, a very useful technique for integrating rational functions. Now here is the basic methodology. Suppose we have a rational function, in this case 1 over x squared minus 4. If the degree of the denominator is greater than the degree of the numerator, then if the denominator is factorable, we might be able to split up that function into partial fractions. So this is what we do here. We say that 1 over x squared minus 4 is 1 over x minus 2 times x plus 2. So we say that this equals a over x minus 2 plus b over x plus 2. We clear the fractions, multiply both sides by x minus 2 times x plus 2. And we get that 1 equals a times x plus 2 plus b times x minus 2. Suppose we let x equal 2. Then we get that a is 1/4. If we let x equal negative 2, then we get that b is negative 1/4. This means that the original integral can be written as the integral of 1/4 over x minus 2 dx plus the integral of negative 1/4 over x plus 2 dx. And these integrals we can readily evaluate. This equals 1/4 times the quantity natural log absolute value of x minus 2 minus the natural log of absolute value of x plus 2 plus a constant of integration. Now if we use logarithmic properties, we can arrive at a very nice function which is actually an inverse hyperbolic tangent function. And if you look at the integral, you see that the inverse hyperbolic function would be the result in this case where a is equal to 2. Now it's very important to look at the degrees of the numerator and the denominator when you're given a rational function. If the degree of the denominator is greater than the degree of the numerator, and the denominator is factorable, then we can proceed as previously done in our last example. But if the degree of the numerator is greater than or equal to the degree of the denominator, we first have to perform longhand division before we can do partial fraction decomposition. Now here is an interesting example. We have the integral of x squared dx over x squared minus 1. So let's rewrite the numerator. Since the degree of the numerator equals the degree of the denominator, we rewrite this as the integral of x squared minus 1 plus 1 over x squared minus 1. This gives us 1 plus 1 over x squared minus 1. So this neat little algebra technique is the same as what we would have gotten using longhand division. So now we can write that integral as the integral of 1 plus a over x minus 1 plus b over x plus 1. And we can integrate readily. We get x plus a natural log absolute value of x minus 1 plus b natural log absolute value of x plus 1 plus a constant of integration. A and B can be found in the same way that we found A and B in our previous example. Now here is the case where the degree of the numerator is greater than the degree of the denominator. So let's take a look at this longhand division that I've mentioned. We write x cubed is divided by x squared plus 9. X squared into x cubed is x. X times x squared plus 9 is x cubed plus 9x. Now subtract. We get negative 9x. So then our integral becomes the integral of x plus negative 9x over x squared plus 9. Now, if we integrate this, it's very easily done. We get x squared over 2 minus 9 halves natural log of x squared plus 9 plus a constant of integration. See, so this is the way we use longhand division to integrate a rational function where the degree of the numerator is greater than that of the denominator. Now let's talk about the Heaviside method. The Heaviside method is a very useful technique in evaluating the coefficients of the partial fraction decomposition. Suppose we have this expression, x plus 6 over x minus 2 times x minus 4 is a over x minus 2 plus b over x minus 4. Then we have x plus 6 equals a times x minus 4 plus b times x minus 2. And the Heaviside method tells us that the values of x being 4 and 2 are the very values we should use to find a and b, just as we did in a previous example. But notice something. When x is equal to 2 and when x is equal to 4, the original expression is undefined. In fact, x equals 2 and x equals 4 are asymptotes for this function. So the function itself is originally undefined at these values. How can we substitute them in order to get the values of a and b? Well, you can prove, using limits, that indeed these are the very values we should use to get a and b. Even though the original function is not defined for x equals 2 or 4, we can use the values x equal 2 and 4 to find the values of a and b. And this is called the Heaviside method. If x is equal to 4, we get 10 equals 2b. So b is 5. If x is equal to 2, we get 8 equals negative 2a. So a is equal to negative 4. And this leads us to the final result of this integral. The integral of x plus 6 dx over x minus 2 times x minus 4 is 5 times the natural log of x minus 4 minus 4 times the natural log of x minus 2 plus a constant of integration. And this completes our discussion of partial fraction decomposition.